So last time we explored the idea of convolutional neural networks with EEG, and I did a little bit of search in terms of trying to find how possibly those data are used today, either if there's a lab who's working with those neural networks, EEG lab, I should say, or any other information. And I found some papers. However, there was one particular lab that caught my interest because the way in which they had used the EEG data was, as opposed to go directly to the raw data that you have, let's say, that you can get from collecting EEG, they had used the images that are being produced from those EEG data. So instead of going to the extracting data from the raw data from the EEG, they extracted the visual representation of what that raw data was about. I thought that was very interesting. So I want to show you, let me share my screen. I want to show you basically what I found about them. So here, their lab is called Mila. And I really like this diagram, and I thought their approach was kind of interesting in terms of here. What I mean is that they're actually using the EEG images as opposed to the raw data. So if we read just this one section that we had, I thought it was very interesting. So they say that one of the challenges in modeling cognitive events from EEG data is finding representations that are invariant to inter or intra-subject differences. That's very important, as well as to inherent noise associated with such data. Herein, we propose a novel approach for learning such representations from multi-channel EEG time series and demonstrates its advantages in the context of mental load classification tasks. First, we transform EEG activities into sequence of topology preserving multispectral images. This is what they mean, as opposed to the standard EEG analysis technique that ignore such spatial information. Next, we train a deep current convolutional neural network inspired by state-of-the-art video classification to learn robust presentations from the sequence of images. The proposed approach is designed to preserve the spatial, spectral, and temporal structure of EEG, which leads to finding features that are less sensitive to variations and distortions with each dimension. Empirical evaluation on the cognitive load classification task demonstrated significant improvement in classification accuracy over current state-of-the-art approach in this field. And here's the map in a bigger sense. I thought this approach was interesting because they're like looking at it from a little bit of a different perspective. Obviously, I don't quite understand everything that they've done, especially in the back end, but judging from this. Having said that, though, there's one thing that I want to bring your attention to for those of you who are interested in EEG data, aka brainwaves, neuroscillation, in conjunction with neural networks. And the thing that I wanted to bring your attention towards is that not everybody is meant to work with the EEG data with neural networks the same way. People choose different ways to explore that area because it's still a very new area. And there's a lot to be learned. So if you are an aspired computational neuroscientist or either or, I do want to bring to your attention that you don't need to follow exactly what they do. Because, for example, the way I think about for me to use EEG data, for example, in neural networks is I'm more interested in actually the parts that they usually is called noise. I'm interested whether there is an information there. Also, I'm interested whether information, how/if the information is transported via those oscillation wirelessly, basically out there or inside, doesn't matter. But that's what I think what I want to say is that it's doesn't have to be the way in which, for example, the traditional way of looking EEG data. You can use essentially neural networks, deep learning, to look at any part of the EEG data that you choose. Traditionally, for example, EEG is used a lot for seizure detection, for example, but I feel like there are non-traditional ways of looking at, or at least exploring the idea of looking at EEG data, which does not, for example, include, for example, seizure detection or ICA or anything else that, workload, classification of EEG workload, etc. So think about it. That's basically, I think that's very, very important. And here's also a little bit of information about their lab. I want to make sure I give credit for that. And then lastly, I wanted to show you this video that bumped into my feed, and I was watching it. I don't know if you know him, but Yann LeCun, who is now working at Meta, but he ends this conversation with something very interesting that also includes, obviously, neural networks in his field. But I thought that these are the type of thought leaders that I think it's healthy for us to listen to in terms of thinking about things differently. I feel like a lot of times when we look at, traditional science, it's very good. They set up the framework for everybody else, for all of us today. But then it's our job to sort of go to the next step. And for me personally, it's been the challenge of thinking big, thinking different. And that is sometimes challenging. And that's why I think listening to, scientists as him, it kind of, stretches my mind and explores it a little bit. So let's actually listen to an excerpt of it. I hope I'm not breaking any copyright laws here, but obviously I'll give credit to this video podcaster as well.
And for some of them, actually more recently, by people like Giorgio Parisi, who just got the Nobel Prize for the replica method, among other things. It's used for different things. Variational inference, that math comes from statistical physics. So a lot of those kind of basic courses, if you do electrical engineering, you take signal processing, you'll learn about Fourier transforms. Again, something super useful. It's at the basis of things like graph neural nets, which is an entirely new sub-area of AI, machine learning, deep learning, which I think is super promising for all kinds of applications. Something very promising, if you're more interested in applications, is the applications of AI, machine learning, and deep learning to science, or to science that can help solve big problems in the world. I have colleagues at Meta, at VAIR, who started this project called Open Catalyst, and it's an open project, collaborative. And the idea is to use deep learning to help design new chemical compounds or materials that would facilitate the separation of hydrogen from oxygen. If you can efficiently separate oxygen from hydrogen with electricity, you solve climate change. It's as simple as that. Because you cover some random desert with solar panels, and you have them work all day, produce hydrogen, and then you ship the hydrogen wherever it's needed. You don't need anything else.
So I mean, I'll send the link so you guys can watch the whole thing. It's very interesting. But the only thing I wanted to emphasize here is the fact that when you start thinking about all these all these possibilities, let me actually when talking about all these possibilities, as he was indicating that the machine learning, deep learning is combined with natural resources. In this case, he mentioned even climate change. So I think that's very important to think about. And in our case, it would be a mashup of machine learning, deep learning, and neuroscience, in this case, EEG, because more specifically, because a lot of things are actually readily available. And so it opens up a lot of new doors for us. All right, so I hope you guys find this helpful. Thanks for watching. See you next time. Bye.